Okay, last week I taught you about this velocity. So on the Bernoulli's equation, I give you the Bernoulli's equation, and also I give you this pressure and force in the liquid. So now I give you the problem for doing. So those concepts I do this, I will solve the problem. For the that's water pipe. So this area is A0 and this area is A. So in this case, A0 is 1/2 centimeter square, A is 0.35 centimeter square. So we have to calculate. So this A0 and the A, this one we this area we like this. So A0 is 1/2 centimeter square, A is 0.35 centimeter square. Two levels are separated by the vertical. This is 0.45 millimeter. The volume flow rate from the test have to be calculated. So the volume flow rate is that you can calculate volume flow rate is equal to the RV. So RV can be calculated. RV is equal to A0 into B0. A0 into B0 is the RV. So we have to calculate the B0. A0 we already know. A0 is 1/2 centimeter square. So we already know it. B0 need to calculate. So B0 can be calculated by the formula. The B0 is equal to the square root of, so B square is equal to B0 square plus 2GH. So this equation, so that we can calculate the B0 here. B0 is square root of the 2GH A square divided by A0 minus A square. A0 square minus A square, so that formula. So this is of the velocity 0 can be calculated by this formula. In this case, A0 into B0 is equal to the A into B. So that formula. This one we have to calculate. So therefore we already know the H and A and the A0. So we substitute, so we call it B0. So B0 we can calculate 2. Here is 9.81. H is 45 millimeter. So 45 divided by 1000. And the A2, so A square. A square is the area I already given is 0.35 centimeter square. So this is 0.35. Divided by A0 minus A square, so 1/2 square minus 0.35 square. So therefore we can calculate the B0. So 0.286 meter per second. So B0 we can calculate. And then you can calculate for the RV. RV is A0 multiplied B0. So A0 is we call it A0 is 1/2 and B0 is 0.286. So therefore the RV is you call the thing with this 0.3 meter per second, so 0.3734 meter per second, centimeter cube per second. So this is called 28.6 0.36 meter per second. So this becomes 28.6 centimeter per second. So here is 1/2 centimeter square. So by solving this one, you got the 34 centimeter cube per second. This is the way, so that this is moving this way. So in this case, theta is 30 degrees. So at this position, these angles are different to this direction to the horizontal surface is 30 degrees. So 30 degrees and surface is moving like this. So in this case, our mass is 83 per kilogram. So this velocity is moving this direction. This velocity is moving this direction. So this began as FD8. So this direction is FD8. So moving this way. So this is the FD8. And here we is the perpendicular. So this direction. So that direction will be the FB. This is our force. So here we is the FB. So FB is this angle with the phi. So here we is this with the mg sin theta. This is the mg sin theta, and this is the mg cos theta. So at the moment we got the equilibrium situation. In this case, that force is equal to mg sin theta, and our force is equal to the mg cos theta. So this is that we can calculate. So FB we can calculate. FB can be calculated. FB is a water force. So FB is a water force. Can be calculated, and MF into G. So MF is a mass multiply volume multiply G. So this is the we can calculate. So in this case, the volume of the this is the rho is the density of the water, B is the volume of the water, G is the gravity. So we substitute here, rho is the density of the water. Density of water is 1.024 into 10 power 3 kilogram per meter cube. We substitute, and also the volume of the water. Volume of the water is the summer volume is 2.5 into 10 power minus 2 meter square. So the volume you substitute is 2.5 into 10 power minus 2 meter cube, and the gravity. So gravitation is we can calculate gravitation is 9.8 meter per second square. So by solving this one, the force can calculate is 2.509, then you into 10 power 2 Newton. So this is for the every we can calculate it. In the meantime, this is for the every we calculate by this way. And also that we also calculate the second law. So this is the FDY, so this direction, this is FDY. So FDY can be calculated by equation. So FDY plus FD is equal to mg cos theta. So that this mg cos theta is go to this direction, FDY and the FD is the upward direction. So that our force and the downward force are equal at the down the equilibrium. So that this is FDY and FD is equal to mg cos theta. So that here we can calculate the FDY. FDY plus FD is we can calculate 2.509 into 10 power 2. Mass is now you saw the mass is 83, G is 9.8, and the cos theta 430. So from here you can calculate the FDY. FDY calculate is 435.5 Newton. So FDY you can calculate. In this case, you also need to calculate FDA. So FDA's formula is FDA is equal to mg sin theta. So the mass is 83, G is 9.81, sin 30. So then you got the FDA is 406.7 Newton. So FDY and the FDA we can calculate by this way. And after that, you can calculate the F. So F is equal to square root of FDA square plus FDY square. So the FDA square we substitute is 406.7 square plus 435.5 square. So then you got that to the force by this way. Thermal expansion. When the temperature is put on any object, so the object will be expanded. So this is the thermal expansion. So there are three kinds of expansion: linear expansion, volume expansion, and the area expansion. So there are three kinds of the thermal expansion. So normally the thermal expansion can be calculated. So firstly we talk about the linear expansion. So linear expansion is a delta L. Delta is a L alpha into delta T. So A is the original length. So alpha is a coefficient of linear expansion, and the delta T is the change of the temperature. L is equal to the original length. So alpha is a coefficient of linear expansion. And delta T, the change of the temperature. So the delta X can be calculated as alpha into the delta T. And also the volume expansion. Volume expansion. So volume expansion also we can calculate the delta V is equal to so the V beta into delta T. So in this case, V is the original volume, and beta is the coefficient of the volume expansion. Delta T is the change of the temperature. So V is the original volume. Beta coefficient of volumetric expansion. And on the delta T is the change of the temperature. In this case, the beta can be calculated. Beta is equal to 3 alpha. And similarly, the area expansion can also be calculated. Area expansion. So it's equal to delta A is equal to A is gamma and delta T. So gamma is a 2 alpha. So A is the original area, delta is a chain of the delta is a chain of the area, and then gamma is the area expansion. So those are the linear volume and the area expansion can be calculated by those formula. We have to utilize the volume. Original QR. Original QR is this volume here. After that, this QR will be expanded. So because of that, weather change volume will be expanded. So the total volume will be original volume plus expanded volume. So the volume has to be calculated. Delta V can be calculated. So this is the V beta into delta T. So the original volume is that we already know that 37,000 liter. So 37,000 liter. So this is the liter. And the beta is the volumetric expansion, the coefficient 9 by 4 into 10 power minus 4 per degree centigrade. 9 by 5 into 10 power minus 4. Multiply the delta T. Delta T is the change in the temperature. Lower than is you have to put the minus. So minus 23 Kelvin. So by solving this answer, further you get the 808 liter. So this is a minus 808 liter. So the final volume, the delivery volume is equal to V plus delta V. So the original volume V is that we already know is 37,000 plus delta V minus 808. So by solving this one, 37,000 minus 808, you got the 36190 liter. So this is for the volume. The volume change to the volumetric expansion of contraction can be calculated as V plus delta V. So in this case, V is the original volume, delta V is the change in the volume due to the temperature change. So we calculate the delta V and add with the original volume, so you get the total volume delivered by the Y cycle. So this one we can calculate by this way. The last topic is the temperature heat. Heat is the energy transfer between the system and its environment because of the temperature difference that is between them. So that when the temperature is changed, so heat will be flowing. So heat will be flowing due to the temperatures are different. So the heat unit can be calculated by the calorie. So calorie is equal to the 3.968 into 10 power minus 3 BTU. We do the British thermal unit, or the 4.186 joule. So therefore we can calculate the heat absorption, heat capacity. Heat absorption or the heat capacity. So heat absorption or heat capacity can be calculated. So in this case, heat absorption capacity is a Q. Q can be calculated as C multiplied delta T. So C is a coefficient specific heat capacity. And delta T is the final temperature minus original temperature. So C multiplied Tf minus Ti. So T is the final temperature. So in also can calculate for the C. C is equal to the multiplied specific heat. So this is the C, the capital C is a small c multiplied by mass. So this becomes as C is equal to specific heat capacity. Specific heat capacity, so the unit will use the joule bar 4910 joule per kilogram Kelvin. 4110 joule per kilogram Kelvin. Kelvin. So this is a specific heat. And it's a mass. It's a mass. Weight the unit weight is a kilogram. So the total heat can be calculated. Q is equal to C into delta T. So that C is a mass multiplied specific heat capacity. Capital C is equal to mass multiplied small c. Small c is the specific heat capacity, and it's a mass. And the change of the temperature is a delta T. So the heat absorbed by the change of the temperature can be calculated, and small c into delta T. So Q is equal to M small c into delta T, or the N small c into final temperature minus original temperature. So this is the way that we can calculate the heat. So that when the temperature change, the heat will be flow. The heat flow can be calculated by that formula. So that Another way is the molar specific heat. The molar specific heat is any substance can be represented by the mole. So 1 mole is equal to the 6.02 into 10 power 23 elementary unit. So the molar specific heat those moles are how much heat can be carry. So this is for the molar specific heat. In the meantime, when the heat change, so the internal saturation can also be changing. So this is because of latent heat. Latent heat means when, for example, the ice. So ice has to absorb some kind of the heat, some amount of heat to melt down to the water. So the 0 degree ice can be transformed to the 0 degree centigrade water. So the original is the solid state of the ice, but the final state will be the liquid state of the water. So same temperature, but the original state is changed to the final state. So solid is changed to the liquid. So the amount of the heat required to change the state is we call it latent heat. So latent heat is the amount of the heat required to change the state. Now how much heat required must be absorbed by the ice or the mass 720 grams at the minus 10 degrees centigrade to the liquid state at the 15 degrees centigrade. So this is the three states. So minus 10 degrees centigrade ice change to the 0 degrees centigrade ice. So this is what is change of the temperature. So change of the temperature, so heat absorbed. So heat absorbed is Q1. The formula to calculate the M into Mi multiplied the Ci multiplied delta T. So this is for the first state. 0 degree centigrade I is minus 10 degrees centigrade ice change to the 0 degree centigrade ice. So this is for the change of the temperature. Another thing is the change of the state. Change of state. Therefore, the 0 degree centigrade ice change the state of 0 degree centigrade water. So in this case, Mi multiplied L is a latent heat. So this is called as Q2. Q2 is equal to Mi multiplied L. So this is a change of the state. And plus saturation, change of the temperature. Change of temperature. So the first is the change of the temperature for the ice saturation. Another one is here is ice to water. And that one will be water to water. So water at the water state, so change of the temperature will also happen. So in this way we can also be calculated Q3 is equal to the M water multiplied C water into delta T. So 3 things we have to add. Q1 plus Q2 plus Q3. So the Q total can be calculated Q1 plus Q2 plus Q3. So the Q1 is equal to the Mi multiplied Ci into delta T. The Q2 is equal to the Mi into L. Q3 is the M water. C water into delta T. So they have to add. So the firstly we have to calculate the Mi. So this we got 720 grams. So this 720 change to the kilogram. So this is the 720 divided by 1,000 kilogram. The Ci is 2220 joule per kilogram Kelvin. And delta T is 0 to the 100 minus 10 degrees. So 0 minus 10. Plus, another thing is Mi. Mi is 720 divided by 1,000. Latent heat of the ice can be calculated. So this is 333 kilos joule per kilogram degree Kelvin. Plus, another one is water. So ice 720 0 gram ice can be done as 720 gram water. So this is the water. If you can calculate 720 divided by 1,000 kilogram multiply. So the C. So C means 4910. C water is 4190. 4190 is kilojoule per kilogram dV Kelvin. Minus delta T. The original is at 0 degree, final temperature is 15. So 15 minus 0. So this is the Q1, Q2, Q3 we can calculate. So by solving this one, key requirement is 300 kilojoule. So this means that firstly the I is a transform, the origin is minus 10 degrees centigrade I. So this is change to the 0 degree centigrade I. And after the 0 degree centigrade I is a change to the 0 degree centigrade water. And from the 0 degree centigrade water, change the temperature to 15 degrees centigrade. So there are three states. Three states, all six states are absorb the heat. So that all the heat combination, we can calculate the heat requirement. This is the copper slab. Mass empty is 75 grams is heated in laboratory oven to a temperature of 312 degrees centigrade. So here we call it slab. Slab we heat the slab and got the final temperature. So this slide is dropped into the glass beaker. So this is the beaker. And then this beaker is containing the water. So beaker is containing this is the glass plus water. So when the slide is we drop it into the beaker, so such temperature will be low. Heat will be low. So heat lost by the slab will equal to the heat gained by the beaker. So in beaker is really a glass plus water. So this is so that there are three things happen. So the beaker to the heat and slab is really the copper. Slab is a copper slab. Copper slab to the heat loss, beaker heat gain and the water heat gain. All are resound to the thermal equilibrium, all are equal to the 0. So therefore the slab here is equal to a QC, and the beaker here is a glass here is equal to the beaker. Beaker is a glass, so QB, and water here is a QW. So we can write down the equation QW plus QB plus QC is equal to 0. So this equation we can write down, and therefore we can write down the QW here. So QW is equal to the CW. NW and the TS minus TI. And also there's a beaker. QB is equal to CB into the this is for the CB multiplies the TM minus TI. And also the copper QC is equal to CCMC into the TF minus TI. So that when you add the source to the final temperature can be calculated. Final temperature equation equal to the Cc into Mc into T plus Cv into the Ti. So this is a capital Cv into Ti plus Cw Nw into the Ti. Divided by Cw Nw plus a capital Cv plus a Cc into Mc. So we substitute here. So by solving this one, our Cc is a 0.0923. And it's a 75 grams. So this is for the and the temperature is 312 degrees centigrade. Plus Cv is a 445 multiply Ti is a 20 degrees centigrade. And here is Cw is a 100 1.00 multiply 220 grams multiply the 20 degrees centigrade. Divided by divided by Cw, Nw, Cc, Cv, and Cc plus Mc. So we can write down here. So this is the CW. So CW will be 1.00 into the NW is 220 plus CV. So CV is 45 plus CC. CC is 0.0923 into 75. So by solving this one, you call it is 20 degrees centigrade. So the final temperature is 20 degrees centigrade. Now we also calculate for the gas system. So gas system is the change of the temperature equal to the multiply the change of the mass, change of the heat. So in this case, PV is equal to the MRT. So this is what P is the pressure of the gas, V is the volume of the gas, N is the mass of the gas, I is this is what the heat capacity, and I is the constant gas constant. So, and also T is a temperature. So here is P is a pressure, V is a volume, I is a gas constant, T is a temperature. So PV is equal to MRT. So this is a equation can be calculated. So also this R and this R can be also calculated. So this is as a K is a Boltzmann constant. Boltzmann constant can be calculated. This is the R divided by N. So R is 8.31 into 8.31 joules per mole into Kelvin divided by and N is 6.02 into 10 power 23 mole per mole. So this is a 5 equation 1.38 into 10 power minus 23 joules per Kelvin. So this is for the K can be calculated by this equation. So the PV is equal to also we can calculate for this NR. NR is equal to this N multiplies K. So this is for the N is the number of the molecule required for the gas, and this is K is a constant. So we can also write down the equation PV equal to NKT. So it is M is the mass of the gas, I is a gas constant, or the number of molecule in the gas is a N, and the K is a Boltzmann constant. And multiplied with temperature is also equal to the P, pressure multiplied volume. So this is the equation for the gas equation. So the gas temperature and gas volume and the gas constant, and the mass of the gas can be related to the this equation, PV equal to MRT or PV equal to the NKT. When the gas is an expansion or contraction, the volume will be changing. So the at the constant temperature, so when the volume change, so there will be the work done by the gas that happen. So this work done by gas at the volume temperature, the initial volume is V1, change to the final volume Vs. So this is the initial volume. And Vs is the final volume. At the constant temperature, so the work done required to change the volume is W. The can be calculated that W is equal to nRT ln final volume divided by initial volume. So we can calculate by this way. Vi, nRT multiply ln Vs divided by Vi. So this is for the work done by the gas can be calculated. In this case, our work done is a W, unit will be the joule. So the gas is the container original pressure, original volume is 12 liter, and temperature is 20 degrees centigrade, and the pressure is 15. So temperature raised to the 35 degrees centigrade. So that this is T5 is 35. Volume reduced to the 8.5 liter. So we have to calculate the final pressure. So in this case, we can write down the equation PV is equal to MRT. So there P into V is divided by T is equal to MR. MR is a constant. And therefore, that we can write down the thing original P1 V1 by T1 is the final P2 V2 by T2. So this is the constant. So that in this case, this problem is that we know the original volume is 12 liter, and the final volume we know, and the original temperature, final temperature. So we have to calculate the final pressure. So the original pressure, we already know that 15. Original V1 is 12. T1 is 20 degrees centigrade, but heat ratio we have to utilize as a Kelvin unit. So 20 plus 273. So 1 degree Kelvin is equal to degree centigrade plus 273. And final pressure P2 is unknown. Volume is 8.5. Final temperature is reduced to 35 degrees centigrade. So this is 35 plus 273. So by solving this one, final pressure P2 can be calculated by this equation. So this is the final pressure. P2 is equal to 22 AF, 22 ATM. In this case, it's given. So in this case, volume expansion. Volume expansion means this is the pressure. Here is the volume. So volume will expand to this way. So you have to calculate the work done. So So this is the W. So W can be calculated. W is equal to the nRT ln VF by VI. So N is we know that one molecule. One molecule of the gas, our value is 8.31 joule per molecule degree Kelvin. And temperature we already know that 310 Kelvin. So the temperature is 310 ln. ln means the final volume where to calculate initial volume. So initial volume as VI is 12 liter and the final volume VI is 19 liter. So 19 divided by 12. So by solving this one, this we call the 1180 joule. So the same amount of the water is done by the gas during the expansion. So in this case, our molecular mass M of the oxygen is 0.0320 kilogram per mole. So that this oxygen's velocity can be calculated. So that this velocity is V average. The formula to calculate is the square root of 8RT divided by the pi into M. So this is the A is the I is the gas constant, T is the temperature, M is the mass of the oxygen. So that this velocity can be calculated. The square root of 8, our value is given as 8.31 joule per mole Kelvin. Degree Kelvin multiplied with the temperature. The temperature is given as 300 degrees Kelvin. So multiply 300, the pi is 3.1416. And the mass is only given 0.0320. So by solving this one, every velocity will be 445 meter per second. So this is for the every velocity we can calculate. And find the root mean square speed of the VRMS. So VRMS equation we can also be calculated. VRMS formula is 3RT divided by the N. So this is the equation. So that this is a 3 I is 8.31, this is 300. Divided by the N is equal to 0.0320. So by solving this one, root mean square speed will be there 483 meter per second. And the C, the phi is the most probable speed will be at the 300 degree Kelvin. So the VB can be calculated. The formula is equal to 2RT divided by N. So this is the equation for the probable speed. Every formula is square root of 8RT by pi N. Root mean square speed is a square root of 3RT by N, and probable speed is a velocity is a square root of 2RT by N. So this is a square root of 2, I is 8.31, P is 300, divided by N is 0.0320. So by solving this one, there will be 395 meter per second. So this is the equation to calculate this three of the oxygen, depending on the temperature, mass, and the gas constant and the change of the temperature. It's an ID species ID gas. So change in the internal energy can be calculated. EM is equal to 3 by 2 N into RT. So it is the N is the number of molecule, I is a gas constant, and T is the temperature. So the when the gas is the sum of the internal energy, change in the internal energy can be calculated by this equation. Okay, last week I talked to you about this